Good afternoon, everyone. My name is Sophie Millen, and I will be explaining the updates that have been made to UKCP09 since the launch. This presentation will include information on the 09 extras, which was originally presented at the users community meeting in November last year. And since then, updates have been made to the weather generator, which will be explained towards the end of this presentation. The UK Climate Projections, UKCP09, was launched in June 2009. Since then, users have asked for a number of updates to be included. And we've talked to our users to establish what was needed and rank the ideas in priority order. DEFRA then funded the top priority updates, which are now available. The updates consist of a combination of extras and enhancements. The extras are those that are completely new, and the enhancements are improvements that have been made to our existing tools. This presentation will focus on the updates in this list, although other updates have been funded by DEFRA. Data and maps based on changes in global temperature have been produced for the UK. These maps can be produced for projected changes across the UK relative to a selected increase in global temperature. All of the information is available through the CSV archive on the user interface, and you'll need to select the text in italics on the screen. The global temperature increases that are available are 2, 3, 4 and 5 degrees Celsius. Only one variable can be examined at a time for 1 month, season or year, and for one probability level. These maps show the projected changes across the UK when the user selects a global temperature increase of 4 degrees. The 10, 50 and 90% probability levels were selected individually to produce these three maps. Like the map showing a global temperature increase, maps for the UK can be produced to show the projected probability of a user-defined threshold. These maps are useful for examining regions that have the same climate thresholds. So this map shows the probability levels when the mean temperature is greater than 3 degrees. It looks at the summer period in the 2070s under a high emission scenario. It shows that for Bournemouth, which is the dark red square in the southwest of England, that there is an 80% probability that temperature is projected to be greater than 3 degrees Celsius under a high emission scenario in the summer. Users asked for projections on fog, snow, lightning and wind. However, it wasn't possible to produce probabilistic projections for these variables, so data was analysed from the 11-member regional climate model and then summarised into separate reports. The methodology for these variables are based on an ensemble of 11 variants of the regional climate model. And unlike the UKCP09 projections, that provide projections of 30-year climates, the RCM provides continuous projections from 1950 to 2099. The RCM data used to produce the reports is available through the Climate Links project website rather than the user interface. For each of the variables, I will explain the key findings, but our technical notes at the link on the screen will provide you with information on our methodology. Like with any variable from the 11-member RCM, only the medium emission scenario is available. For fog in the 2080s, projections show a general reduction throughout the year. For winter, fog is projected to decrease by more than 50% in northern Britain and northern Wales, but is projected to increase between 1 and 30% over southern and mid-England. For spring and summer it is much the same, but with larger reductions. And for autumn, projections show reductions of 10 to 30% across the UK, with higher reductions over the Scottish Highlands. For snow, projections show a reduction across all regions. The largest reductions are for spring and autumn, which are projected to be greater than 70%, and for winter, a 40 to 70% reduction is projected for the 2080s. For the whole of the UK, the reductions in snow events may be greater than 80% for winter and autumn, and greater than 40% in spring. Lightning projections for the 2080s show an increase in the number of lightning days across the UK for all seasons. Projected increases are largest in the summer, and there is a north-south divide of change, with projected increase greatest in Scotland and Northern Ireland and smallest in southern England. Projected increases in autumn are largest over South England and Wales, and increases in spring and winter are small in all locations. For wind speed, the 11-member RCM projections can be characterised by lower than observed wind speeds over mountainous regions of Scotland and Wales, and higher than observed wind speeds over low-lying regions of England. Projected changes in 30-year averages are relatively small within the RCM. Seasonal changes at individual locations across the UK lie within the range of -15% change to +10% change. I've explained the maps based on global temperature change, the maps of probability for a given threshold, and the technical notes on fog, lightning, snow and wind. I'll now move on to explain the spatially coherent projections, the probabilistic wind information, and enhancements that have been made to the weather generator. The spatially coherent projections, or SCPs, provide projections of climate change and absolute future climate for 11 ensemble members. These are available for annual, seasonal and monthly climate averages at a 25 km grid square resolution. They are available for 7 30-year time periods and for all 3 emission scenarios. The SCPs are available in CSV format from the CSV archive on our user interface. The SCPs are based on the ensemble of regional climate models that were used in the making of UKCP09. They were developed by applying scaling factors to the RCM data. They provided users who needed spatial coherency in the data, but who also wanted to incorporate the wider set of uncertainties available through UKCP09. There is a larger range of climate variables available through the SCPs than UKCP09, but they're not a replacement for 09. As I explained earlier, when UKCP09 first launched, it wasn't possible to provide probabilistic projections of changes for certain variables such as wind speed, because wind wasn't available from other global climate models. However, it was found that the monthly mean wind speeds from the ensemble of other climate models could be estimated by accumulating values of wind speed calculated from the daily means of the westerly and northerly components of wind. Probabilistic projections of wind speed are now provided as part of the 09 extras. The last slide explained projections for surface wind speed, which is from the 11-member RCM. This slide explains probabilistic projections of wind speed, which are now available from the 09 CSV archive. In summer, wind speed for the 2050s covers both positive and negative changes, but slightly skewed towards negative changes. The 50% probability level shows a tendency towards a small reduction in wind speed, with changes over most of the UK being between -0.2 meters per second and 0 meters per second. For winter, the ranges of anomalies in wind speed are around near zero change, with the 10 to 90% probability range typically around -0.5 to +0.5 meters per second. The spread in changes in wind speed are greatest over Scotland, where there remains larger ranges of uncertainty. The weather generator is a statistical tool that has downscaled the 25 km probabilistic projections to produce daily and hourly time series at a 5 km grid scale. A new version of the weather generator was developed because there were limitations with the original version that could be improved. Version 2.0 includes 4 major amendments and replaces the original weather generator. Old jobs can still be accessed, and requests can be made through the help desk to run a job through the original version. There is also guidance for the updated weather generator on the 09 website, which you can access from the home page. The 4 amendments to the weather generator are changes to the rainfall and temperature extremes, an improvement in the number of sunshine hours in a day, and changes to the baselines for sunshine and vapour pressure. The original weather generator underestimated hourly extreme rainfall. This was possible because a simplified rainfall model had been used to make it as robust as possible. To improve the performance of the rainfall extremes, a number of different distributions were trialled before a gamma distribution was selected to be the best. The series were then analysed at a range of return periods and durations and validated against depths taken from the Flood Estimation Handbook. The results were found to be more consistent than the previous method, which used an exponential distribution. These graphs show the comparisons between the weather generator rainfall estimates and the Flood Estimation Handbook depth duration frequency model estimates. The graph on the left is the daily resolution, and on the right is the hourly resolution. The weather generator team have chosen a site in North East England to illustrate these results. So as you can see here, there was previously an underestimation of up to 50% found in the 30-year return period. Now these graphs show the estimates are within the 90% confidence limits, which is a vast improvement. You will also see that the weather generator performs better at daily, which is on the left, than at hourly on the right, and there was a very good fit to the Flood Estimation Handbook model with the daily. Daily maximum and hourly extreme temperatures were also underestimated. This has been improved in two ways: the addition of a dry spell transition and the use of a different temperature distribution. The next two slides will explain this in more detail. The original weather generator had 4 different 2-day sequences: dry today, dry yesterday, wet today, wet yesterday, dry today, wet yesterday, and wet today, dry yesterday. However, it didn't simulate the build-up of temperature during longer dry spells. For example, if a 2-day dry spell fell between 2 wet days, it would show the same results as if it were part of a longer dry spell. Because of this, the weather generator tended to underestimate the daily maximum temperature values during successive dry days. So this scenario in real life would tend to result in maximum temperatures building up each day with minimal overnight cooling in between. The weather generator team therefore added a 5th sequence of days: dry today, dry yesterday, and dry the day before, which has improved the performance for maximum temperatures and heatwave duration. The original weather generator assumes a normal distribution for the baseline temperature of 1961 to 1990. However, temperature extremes can sometimes cause the distribution to skew, so the weather generator team have applied a calculation to the data. They have validated the results using observed data, which has shown that the problem in the original version has been alleviated. Moving on to sunshine hours, the original weather generator estimated daily sunshine producing values from the moment the sun rose above the horizon. This overestimated effective sunshine because observational equipment does not begin recording until the sun is higher in the sky. And to deal with this, modifications were made to include a more realistic and slightly shorter day length. Version 2.0 now more accurately reflects how sunshine has been measured in the observations. Last year, users noted that outputs from the weather generator showed inconsistent changes in future sunshine hours when compared to changes in future cloud cover. It was also discovered that there was a related issue with vapor pressure, although the effects here were smaller. It's important to note that these issues are not to do with the probabilistic data or the original version of the weather generator. They're due to the choice of the observed baseline climatology used to make the change factors. So how has it changed? The weather generator team have set up a new observed baseline. The baselines were originally calculated from observed data, and now they have been derived using calculations. Most of the variables required in the change factors are available in the projections, but sunshine and vapor pressure are two that are not part of these basic variables. They have therefore had to be calculated from variables that are available, such as cloud, relative humidity, and temperature. So for sunshine, the calculation of 1 minus cloud has been used, which remains constant for the baseline and future climate, and for vapor pressure, observational relative humidity and temperature have been used. These amendments now show more realistic changes. If you have done analysis of the extremes, it is recommended that you rerun your analysis with version 2.0. Sunshine and vapor pressure have changed. The average statistics and properties should not have changed significantly, so there is no need to rerun the weather generator. The most important thing to remember is to reference which version of the weather generator you have used in any report and label all your outputs as version 1.0 or 2.0 so that your methodology can be replicated. I hope that this has been a useful presentation. We'll take any questions now.